Okay, good morning. Welcome to
FamilyMath number 123.
FamilyMath number 123. So there was an amazing coincidence on Twitter yesterday. Yesterday morning, you and I talked about the continued fraction for the square root of 2, right?
Yeah.
And then on Twitter last night, someone, Miss Patrick Hunter, posted a really cool proof from geometry that the square root of 2 is irrational. And our fractions that approximated the square root of 2 came into that proof. They showed up in there. So I thought that was really cool, and we would talk about that today. So first we said that the continued fraction 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 ... forever. This was the square root of 2. And you could probably use this to prove that the square root of 2 is irrational as well, by the way, but we're not going to do that. But these, if you stop and do if you stop at every point where there's a 1 over, you get 1, 3/2. If you do it here, you get 7/5, 17/12, 41/29. And there was an even easier way to see that with our little special continued fraction machine.
Yeah.
But again, I don't want to talk about today. Do you remember talking about continued fractions when you were a couple years ago? Okay. So here's the other proof that they were talking about, and we're going to see how our fractions come in, like 17/12 and 41/29. Okay. So they say assume the square root of 2 is a over b in lowest terms.
So it's proof by contradiction.
Yeah, it is proof by contradiction. We're going to assume it's a over b, where a and b are integers in lowest terms. Okay.
Right.
That means that 2, if I square both sides, 2 is a squared over b squared, right?
Yeah.
And then a squared equals 2b squared. That's what that would mean.
Yeah.
Okay, and this was the smallest numbers that made this work, so that it was in lowest terms. Okay?
Yeah.
Now, if a squared equals 2b squared, that means I could take a square with side a and turn it into 2 squares of side b. And unfortunately, I didn't draw the ratios quite right, but that's what that would mean. The area here, which is
A squared.
a squared, would equal b squared plus b squared. I could break this square up
into 2b squares.
into 2b squares. Okay?
Alright.
Now, since I didn't draw it right the first time, let me try to draw it a little better. But this time I'm going to put the b squares inside. Okay? One would be about like that.
Yeah.
And one would be about like that. And the other, oh God, sorry. Doing this in the morning, it'd be up here in this corner like this. That's what I'm not getting it right. And I'll put the other one down in this corner.
Yeah.
Okay?
Yeah, but there's that square intersecting the middle.
Right, this square overlaps and I don't get this or this. Okay?
Yeah.
Now, since these two squares have to add up to the whole bit,
Yeah.
that means that the part I counted twice,
Yeah, but it.
which I have to subtract away, right?
Yeah.
Let me call this d squared, because it's a square.
Yeah.
And then call this c squared and c squared. That means c squared plus c squared minus d squared has to equal 0.
Yeah.
Because this square plus this square, we already said, added up to the whole thing.
Yeah.
Okay? Now, if c squared plus c squared minus d squared, minus the part that overlapped, equals 0, that means c squared plus c squared equals d squared. Oh, wait a minute. Or 2c squared equals d squared. And c and d are smaller than what we started with, right?
Yeah.
Yeah.
But we said we started with the smallest one.
What?
Ah!
Uh-oh.
Uh-oh. And by the way, they're also going to be integers because this side was an integer.
Yeah.
And this side here is an integer.
And then you can keep chopping it up into smaller.
Right, so I made smaller squares with integer sides that worked.
But we said it was the lowest term.
But we said it was
there was lower terms.
right.
Yeah.
We said it was the smallest one, but then we made a smaller one. So that means it can't. Our assumption that it was rational was wrong.
Yeah.
Okay.
So it has to be irrational.
So it has to be irrational. But now, this is where things get really cool from what we talked about yesterday, and you'll see why I still haven't drawn this quite right. Let's use 41 over 29. Okay, for the big one. So the big rectangle is 41 from top to bottom.
No.
And this small rectangle is 29.
29.
Okay. How much more do I have to go to make this 41?
It's 12.
12.
That's.
Okay. And that means this part up here is 12.
Yeah.
And this part here is 12. This is 29, 29, and 12, right?
Yeah.
Okay, now how much do they overlap? Well, if I go 29 this way and 29 this way, how big is the overlap here?
Well, it's gonna be.
Let's see, so
It's gonna all add up to 58, and you just have to subtract something that's 17.
So this is 17. So you can see why I drawn it wrong. I've drawn the square that's 17 by 17 by 17, smaller than the 12 by 12 one.
Yeah.
So that's just, okay, whatever. But this one's 17 by 17 by 17 by 17. So we started out with 41 and 29. And what new set of squares did I produce?
You have 12 and 17. Hey.
17 and 12.
Hey, it looks like we can keep going down this list.
We
until
keep
reach
going
1
all
over
the way down.
until we reach 1/1.
Right. So isn't that cool? So if I started with 17 and 12, this overlapping rectangle would have been 7, and the ones over here would have been 5.
And then then it would be 3 and 2, and then it would be 1 and 1. That's cool.
Yeah, that's really cool, right? So these fractions, which are called the conversions in the continued fraction, actually have a really neat geometric interpretation. And it kind of helps you understand the square root of 2.
Yeah.
Pretty fun, right?
Yeah.
And that was all just a fun little coincidence on Twitter yesterday. Can you believe it?
Wow.
Wow.